Um, Hi, this is the Elon's Dog MEC 203 project, and this is the introduction. So for the Mars rover project, me, Franklin Blanco, and Sudipto Mazumder worked together to create Elon's Dog. And as suggested, this was inspired not only by NASA's Mars rover, but also a dog, as you can see it configured in a dog-like shape. And when we were building the robot, many criteria had to be respected, such as the 3 by 3 by 3 meter dimension restriction and a lightweight design in mind.
Some key highlights of our design include the robotic arm/claw, which is meant to assist the robot when picking the objects up, the solar panels, and the plutonium enclosure, both of which help provide sufficient energy to the robot to keep it up and running. The wheels with the protective layer of tread in order to protect the rover's wheels as it traverses through the rough terrain of Mars. The suspension to help keep the wheels attached to the robot, and the camera assisting the robot to analyze data on Mars.
And then the assembly of Elon's dog is that the robot is assembled just as one would expect it to. The wheels are connected to suspension that is connected to the chassis of the robot. There are six wheels and two suspensions in total. The solar panels and the plutonium reactor can be found connected to the chassis of the robot. This is convenient because the solar panels need to be in a location where it could easily detect sunlight to maximize its utility. Since the chassis was big, it was also an option to place a plutonium reactor. This conveniently ended up being our final location for the engine. Lastly, the camera and the arm were placed in areas where they would maximize your utility since they complement each other so well. Thus, the camera was chosen to be placed on the left of the chassis with the base of the robot arm placed directly underneath it. The camera can easily detect objects with a 360-degree rotation, and since the claws act like pincers, it can do its job of attaining objects for further analysis extremely well. And then the first motion gen study will be of the wheel.
The wheels have a H7K6 locational transition fit with a shaft tolerance of 0.011 millimeters and a hole tolerance of 0.018 millimeters. It lines up with the hole basis shaft basis system for the suspension really well because the wheel hub wants to lock into place once connected with the suspension and the wheel, allowing for compromise between clearance and interference and providing overall stability by preventing implosion of the wheels.
And then the next motion gen study will be of the solar panels.
The solar panels have a H7G6 sliding fit with a shaft tolerance of 0.013 millimeters and a hole tolerance of 0.021 millimeters. It's great for allowing the solar panels to slide on the cylindrical surface on top of the chassis to turn and locate to sunlight more accurately and efficiently.
And then the third motion gen study will be of the claw arm.
The joints in the claw arm have a H7H6 locational clearance fit with a shaft tolerance of 0.008 millimeters and a hole tolerance of 0.012 millimeters, allowing the pincers to move and rotate freely.
And then the last and final gen study will be of the rotating camera and the mask.
The joints in this camera have a H7G6 locational sliding fit with a shaft tolerance of 0.013 and a hole tolerance of 0.021 millimeters, allowing the camera to rotate 360 degrees.
And then that was the last motion gen study, and then that marks the end of the MEC 203